Hey kids, we're going to do day 2 notes, and I'm going to pull these up here, and we are going to attempt to use the Mobi. So what that does is that allows me to write on the screen. So let's see how that works. I'm not real good with technology anyway. So, all right, so measurement day 2. So accuracy. People get accuracy and precision confused with one another. They think they mean the same thing, and they really actually don't, especially in science. So accuracy in science refers to how close a measured value is to its accepted value. So if I know that gold has a density of 19.3 grams per cubic centimeter, and I measure a sample of gold, and I find that it's 19.1 grams per cubic centimeter. Well, that means I'm pretty darn close, so my measurement is accurate because it's close to the known value. Here, this person who's practicing with the bow and arrow, what do you think would be the accepted value for a target, for a bullseye, for this archery target? Right, it would be the bullseye. So the closer someone is to the bullseye, the more accurate a shot they are. It looks like only a few arrows here hit the bullseye. They're accurate enough, but it looks like they're kind of all over the place. They should probably practice some. Precision has two meanings. So accuracy is how close a measured value is to its known value. Precision, again, has two general meanings. Precision refers to how close a series of measurements are to one another. So how many times did I measure the density of gold and get 19.1 and other measurements close to 19.1? Did I get 19.1 and 19.9 and 19.3 and 19.2? Well, in that selection of measurements, I'd only have 3 of them that are close to one another. So I'm pretty precise. I've got one outlier, but I'm pretty precise. The word precision also is used to indicate how exact a measurement is. So what that basically means is the more numbers past the decimal point, the more precise the measurement is. If I'm just eyeballing from here to the window, I could say, oh, it looks like it's about 30 feet. But if I used a meter stick, I'd be able to measure it much more precisely. I'd be able to say, no, it's not 30 feet, it's 29.7 feet. You know, I'd have one number past the decimal point. My instrument is able to measure that precision. That measurement would be more precise. Over here, if you look at the targets, it looks like that person is both accurate and precise. They're very good getting it in that bullseye all the time. Okay, different measuring devices have different uses and different degrees of precision. So it just depends on how much precision you need in your lab. Okay, first thing that we see there is a graduated cylinder. You guys have probably used those before, and it's fairly accurate. It's got the 10s marked and then the 1s marked, and there's little spots in between. A syringe would be very, very accurate or very, very precise. You'd have to measure really small amounts in a syringe. Think about the medication, like if you got a shot, has to be really super precise, has a lot of little divisions on it. There's a burette there, and a burette's not something that you guys have used before, but it's used for measuring out very precise volumes. It has a lot of little marks on the sides, little subdivisions, so that means it's very, very precise. A pipette is not precise. It's usually only has one mark on it, and it's maybe for a 5 milliliter volume or maybe a 10, but it's usually not terribly precise. It usually will just have 1 or 2 marks on it. A volumetric flask, same thing. Usually that only has like 1 marking on it, so it's not as precise. But if you were asked which of these instruments would be most precise, I'd have to go with probably the burette is probably the most precise because it's got the most number of little markings on the side. Which of these do you think is more precise? A, the graduated cylinder, the beaker, or B, the graduated cylinder? Yeah, it's B because it has more markings on it. Okay, you're looking at the number of little markings or subdivisions that are on the device. Since it has more of those, it's a more precise measurement. Okay, so if we're reading instruments, you read the instruments to the smallest subdivision that you see. So whatever's the line that you see. And then you have to estimate the distance in between the two lines, the two smallest lines. Sometimes that's kind of tricky to do. That when you're estimating where the measurement is in between those two smallest lines, that's going to be your estimated digit. Okay, because there's really not any number right there. Here, let me click on this, get you the highlighter. So there's really not any number right here, okay, in between. You can measure this, you know, you see that that's 1, and then you can count these little subdivisions. You can count 1, 2, 3, 4, 5. So we know that it's more than 0.5 because that's where the measurement is. That's where that arrow is. Okay, we know it's more than 1.5, but it's also less than 1.6. So that number that's in between those two lines is an estimated digit. Okay, it is estimated in there. So you guys think for a second, what do you think that measurement would be? You know it's 1.5 something. What would be the digit that you would estimate? Well, I erase that for you. There's a 1. There's the 5. So what do you think? 1.54 estimated digit? I'm going to go 1.54. I keep clicking and it's not clicking in. There you go. 1.54. So 4 would be the estimated digit. Let's go back 1, 2, 3. I'm going back to our slide. There we go. Okay, so 1.54 is the measurement. 4 is the estimated digit. We estimated the spot in between the 5 and the 6. Okay, so that's the estimated digit. All right, dimensional analysis is the most useful tool that you'll ever learn in chemistry. You'll use dimensional analysis not only in chemistry, but when you go off to college, it's a really useful tool for converting units. Okay, it's going to feel like math, and you're going to use a calculator, but it's not math. It's unit conversions, and I'm going to show you how this will work. Dimensional analysis is also called the factor label method, but we call it dimensional analysis. One of the most useful math tools you'll ever learn. What this is all about is just conversion. It's converting one thing to another. You just have to be able to have a conversion factor, which we'll learn how to do that too. We'll get a bunch of conversion factors. Okay, anything that you measure will have a number with some sort of unit of measure. You don't always think of it as a unit, but it'll have some sort of unit to go with it. A unit could be miles, gallons, miles per second, peas per pod, or pizza slices per person. Okay, that could be a unit of measure. It could be a conversion factor for us. Dimensional analysis is a way to calculate how many pizzas I need for a party and how much it's going to cost me. How to determine how many light years there are in a football field. Ha, did you catch that? Because I paused the recording and answered the phone. I feel like I'm a technology genius right now. Okay, so let's get back to it. Dimensional analysis. You could discover how many centimeters are in a mile if you're crazy enough to really want to know that. How many dollars per mile your gas costs. You guys are going to want to know that because you're probably getting your permit, or some of you guys will be getting your license soon, and gas is a real thing. You have to buy gas, so that can be a problem. So conversion factors. What are conversion factors? They're unit factors also, but I call them conversion factors. Before we can get started with dimensional analysis, we need to have a set of conversion factors. Converting units is the whole thing to dimensional analysis. Now, I told you it's going to feel like math. It's not. It's all about converting units. Therefore, the units are important, and they have to be written every step of the problem. If you don't write the units every step of the problem, I'm not going to be able to figure out, if you keep getting the wrong answer, where you need help, because I'm not going to know what you're doing. So it's really important that we write the units every single time. Dimensional analysis definitions. Okay, some things that you'll hear me say. An equality, an expression that means this equals that. So the equality will be whatever's on top will be technically equal to whatever's on bottom. The units will just be different. Like right here we see 1 hour is equal to 60 minutes. Well, you know that when somebody says 1 hour, you know that's 60 minutes. Or if somebody says it's 60 minutes, you know that it's an hour. That's an equality. They mean the same things. They're equal. A conversion factor is a ratio of the equivalence in an equality. Now, a lot of times you guys are used to seeing ratios with the two little dots in the middle. That's not how we write the ratios for conversion factors. You write them, you set them up like a fraction. Here we have 1 hour is equal to 60 minutes. We set up the conversion factor this way, or we can set it up this way. It could be either way. It just depends really on the needs of your problem, and you'll be able to tell. I'm going to teach you how to tell which way you would put that conversion factor in order to get your answer correct. But notice these are different ways of saying the exact same thing. A unit conversion factor is a ratio whose numerator and denominator are equivalent measurements. Some common unit conversion factors are given below. You can also use the reciprocal of these. So how many inches are in a foot? 12. How many feet in a yard? 3. How many feet in a mile? Do you not know that? Some you do, some you don't. 5,280. How many ounces are in a pound? 16. 16 ounces are in a pound. How many cups are in a pint? Well, we're starting to get to where I am not really good with these. So let's go here, and there you go. 2 cups in a pint, 2 pints in a quart. I did know that one. 4 quarts in a gallon. I knew that one. Let's see. 1 hour, 60 minutes. Yup, knew that one. 1 minute is 60 seconds. 1 meter is 100 centimeters. These two on the end, you're going to need to know those metric conversions. You're going to need to know that 1 meter is 100 centimeters. You're going to need to know that 1 kilometer is 1,000 meters. Those are going to be important for you guys to memorize. Other conversion factors. Here's ones that we use all the time. We know all these. We just went over most of them on our last slide. So questions that you'll have when you're working your problems. The first question, what's the question asking for? What is my given in the problem, and what unit should be in the answer? So you'll need to know what your given is and look at the units for your given. Number 2, what's the given unit? Number 3, which conversion factors do I need to use? Do I know what a conversion factor is for whatever it is that I'm using, my given? Oops, sorry, didn't mean to do that. Click there and there. So our first example problem, how many seconds are in a day? Sometimes it seems like a million, seriously. But let's see. Is it a million? Could be less, could be more. Let's see. So what do I know? Well, what I know is I know that 1 day is 24 hours. I know that 1 hour is 60 minutes, and I know that 1 minute is 60 seconds. But off the top of my head, I do not know how many seconds are in a day. So these are some conversion factors that I can use. What is my given? Right, 1 day. When we're doing these problems, here, let's get a pen. When we're doing these problems, I'm going to ask you to box your given. Box your given and circle your unknown. Let's see. How many seconds are in a day? Which one's my unknown? Seconds. That's what I'm looking for. Okay? Box the given, circle the unknown. That way you'll always know what you're doing. Okay? It's going to ask me, no, I don't want to insert this. So what do I want to know? I want to know seconds. What am I given? I'm given days. And what conversion factors can I use? I can probably use all of these. How do I choose a conversion factor? Write the given with the units over 1 or leave the denominator blank. So in the very first block, what you're going to do is you're going to write the given with its units over the number 1, or you can leave that denominator blank. Number 2, write the first conversion factor. So you're going to write the conversion factor with a given unit on bottom, and I'm going to show you in a minute why you do that. So you use that first conversion factor. Make sure that your given this time is on bottom. If your answer unit is not on top, or if your unknown, the unit for your unknown is not on top, we're going to have to use multiple conversion factors. No problem. You can do this. Trust me. You guys you'll be great at this. Check your work by canceling units as you go. I always do that. Always cancel my units as I go. So dimensional analysis is a method of problem solving that helps convert between the units. So here I told you what you're going to do is put your given with the units on top. So I'll put whatever the number is in my problem of my given, and I'm going to put the units next to it. Then I'm going to write my conversion factor, but I'm going to put it so that the given is here on bottom in the denominator. And my unknown, or what I'm trying to find with its units, is going to be in the numerator. This is the way to do it. You can use it as a T-chart. A lot of times I don't. I don't use a T-chart. I use down here, I just multiply, because that's what you're doing anyway. I'll write my given with the units, and then I'll multiply by my conversion factor here with the given units on bottom and the unknown on top. And it's exactly the same as the way we do it in the T-chart. It's just a preference for you. You can do it however you want to. Okay, so what is that? That's your given, and then you have your unknown. Let's see, click through that. There's my conversion factor. Let's see, with the given on bottom. Okay, how many seconds are in a day? We're back to our example problem. We're going to get to it eventually. Write the given with the units over 1. Write the first conversion factor with the given unit on bottom. If your answer's not on top, we'll use another conversion factor. Check your work. Cancel your units. You'll see. Watch. Say 1 day. 1 day was my given, right? So then I have to multiply by a conversion factor where day is going to be in the denominator, and a conversion factor that is equal to day is going to be on top. So what did we say was equal to a day? Did we know how many seconds? No, we don't. Do we know how many minutes? Probably not. Do you know how many hours? Yep, 24 hours in a day. So that's the first conversion factor. See what I did? I have day in the numerator day in the numerator right here. There's my given. Then my conversion factor has day in the denominator and has my unknown. It's not what I'm getting to, but it's the intermediate conversion factor until we can get to seconds. So days will cancel if I do it that way. Mathematically, you know that. If you have a unit in the numerator and then you put the same unit in the denominator and you multiply, those units are going to cancel. So that's what we did. Okay, we're going to multiply by another conversion factor that gets us closer to seconds. Okay, I know that in an hour there's 60 minutes, and then I can do my seconds because I know what? Yep, I know how many seconds are in a minute. So what I do each time here, let me show you. We get a pen or highlighter. There we go. Each time, whatever I have here in the numerator goes in the denominator. Okay, I wasn't ready to go to seconds, so I had hours right here. So I knew hours had to go down here. Okay, I didn't want minutes, I wanted seconds, so I knew minutes had to go down there. All right, you do that until you have the unit that you're looking for. This one right here, seconds. You have seconds right there in the numerator. When it's in the numerator, you can stop and you can do the math. Let's see if I can remember how to do this. No, I don't want to keep it. Okay, so what I'm going to do at the end, I'm going to multiply everything that's in the numerator and divide by what's in the denominator. Okay, multiply all the numbers on top. So technically 1 day is in the numerator. So you'd multiply 1 times 24 times 60 times 60. And then you'd put that in the numerator. Then you'd multiply everything that's in the denominator together. 1 times 1 times 1 is 1. So divide the top number into, or divide the top number by the bottom number. So 1 divided into anything is itself. So there you go, 86,400 seconds. Probably no information you ever wanted to know, but now you know. Okay, how many hours are in 1.5 years? Okay, so what's my given? Remember I told you, what are you going to do? You are going to box the given and circle the unknown. Box the given, 1.5 years. How many hours? That's my unknown. Hours is my unknown. Okay, box the given, circle the unknown. What's the given? 1.5 years. What units do you want to know? Well, I want to know hours. What equalities do I have going from years to hours? Well, I know that 1 year is 365 days. I also know that a day is 24 hours. Sometimes a day is 24 hours. Sometimes a day feels like it's 80 hours. Write the given with the units over 1. So over here, we're going to put years. How many years was it? It's 1.5 years. Then you're going to write your first conversion factor. Okay, there's 1.5 years. Now my first conversion factor is going to go here. So if years is in the numerator, it needs to go down here in the denominator. Do I know how many hours are in a year? Nope. What do I know? Yep, I know how many days are in a year, 365 days. Don't give me the leap year stuff. I know that. 365 days is what we're going with. Okay, well that doesn't get me to hours yet. So I do know that there's 24 hours in a day, and that's going to be my last conversion factor. 24 hours in 1 day. Well, now that I have hours in the numerator, here I'm trying to find my cursor. My cursor's lost. There we go. Yeah, it's lost. There we go. I'm going to multiply everything in the numerator, and I'm going to divide by everything in the denominator. So look, what do I have? 13,140 hours. I got that by multiplying 1.5 times 365 times 24 and divide by 1. Okay, then you've got hours. See? Not that hard. All right, back to the pizza party. We're going pizza party now. You're throwing a pizza party for 15 people and you figure that each person might eat 4 slices. Depends on the size of the pizza. How much is pizza going to cost you? Because you have a little part-time job at the movie theater, but they don't pay all that much. So you need to figure out how much it's going to cost. Do I need to hit mom up for money? You call up the pizza place and you learn that each pizza will cost you $14.78. Why? Because you went to Grimaldi's instead of going to like Little Caesars. All right? Use your head, people. Go to Little Caesars. They aren't $14.78 there. But for the purposes of this example, we went to Grimaldi's and got good pizza. That pizza is going to be cut into 12 slices. Okay, so I've got some numbers in here. I've got some conversion factors. You tell them, hey, I'm going to check with my mom. I'll call you back. Do you have enough money? Well, here's how you figure that out. What question do I want to answer? I need to know how much party's going to cost. Okay, what are my units? What would my unit be for cost? Dollars. Duh, dollars. What are my givens? Well, I know that I'm inviting 15 people. That's really my only given. Okay, everything else is a conversion factor. What's the conversion factors that are available? Well, let's look. There's a bunch of them. There's going to be 15 people at the party. So 15 people in one party. Each person eats 4 slices. So 4 slices, 1 person. Okay, that's a conversion factor. Ooh, cursor again. There we go. We know that there's 12 slices in one pizza. So we've got some conversion. You can see how this is going to work out. And you guys could probably do this on your own without dimensional analysis, but this is just a way to teach you. We also know that each pizza costs $14.78. Okay, look what we can do. One pizza is $14.78. We could also turn that upside down and say $14.78 in one pizza. We can use all of these conversion factors at the bottom any way we need to. It doesn't matter. You can flip the conversion factors because remember, each conversion factor equals 1. The whole thing equals 1. So you could flip it if you needed to. So let's keep going and see what we got. Okay, so 15 people was my given. Then I use a conversion factor. Well, there's 4 slices per person, so people and person, that'll cancel. Okay? Now I need slices. Well, I've got slices in the numerator. What did I want? I wanted dollars. So I need to go closer to dollars. Well, I happen to know that there's 12 slices in one pizza. So slices will cancel. Then I happen to know that one pizza is $14.78. So look what I did. I've got $2 in the numerator. I've managed to do this all the way. Everything cancels. Here, let's get a, let's get a pen. Okay? People cancel. All right? Slices, cancels. Pizza, cancels. And I'm left with $14.78. I'm left with dollars, which is the unit that I was looking for. I multiply 15 times 4 times 1 times $14.78. And in this case, I'm going to divide by 12. Look at the denominator. 1 times 12 times 1. So I'm going to divide the denominator into the numerator. I get $73.90. Do we need to ask mom for money? Probably so. Okay, no, I don't want to keep that. Okay, so this is where it's going to get tricky for me because I'm going to have to use technology with a pen. So let's see if I can do this. You got to be patient with me. All right, a 5-kilometer run is 3.1 miles. How many meters is this? So let's see. Let me see if I can do this. 5-kilometer run is, let's see, let me find my pen. Oh, gotta turn it on. Here, let me pause you for a second. Okay, so I've got my pen ready. We're going to see if it'll work. 5-kilometer run, 3.1 miles. How many meters is this? Okay, so here we go. What is my given? 3.1 miles is my given. So I put a box around it. What's my unknown? What am I looking for? Well, I'm looking for how many meters is that? So I circle my unknown. I start my problems by writing the given. So I do 3.1 miles. Okay. Do I need to put it over 1? No, I don't have to, but I can. But I don't have to. I know I need a conversion factor. So 3.1 miles, I need to find a conversion factor. Well, up here underneath my recording, it says that 1 mile is 1,609 meters. So I've got miles in the numerator. I put miles in the denominator. Okay. and then I put my conversion factor, meters, in the top. There was 609 meters in 1 mile. Okay, miles will cancel, and I'm left with meters. I'll do 3.1 times 1609. Let me get my calculator. There it is. Okay, so I'm going to get my calculator and clear it because I'm in a weird mode. 3.1 times 1609 gives me, you can't see that, 4,987.9. So that gives me 4,000 what? 987.9. Wow, that's a lot of numbers. Okay, so 4,987.9. What's the unit? Right, meters. Okay. See over here, John Travolta. Do you guys ever watch that movie? Saturday Night Fever? It's really old. Like, I was a kid when Saturday Night Fever came out, so that's how old it was. So what we tell you to do when you're using dimensional analysis, we tell you to disco down the units. Okay, right here, the unit miles, disco down that unit. Okay, miles there, miles down there. Disco down the unit. Okay, there we go. All right, so that's what disco down is. That's why that's over there. So we're not weird. We're a little weird. Okay, so let's try the other problem. A 10-kilometer run is 6.2 miles. How many centimeters is this? Okay, 6.2 miles is my given. So I'm going to box it. I'm circling my unknown. What am I looking for? Yep, I'm looking for centimeters. So let's see. I start by writing my given. 6.2 miles. Okay, disco down the unit. So I do this, disco down the unit. There we go. Miles. So I'm going to put miles down here. And what am I looking for? I'm looking for centimeters. Well, did my conversion factor tell me centimeters? No, it did not. It told me meters. So we can do that. No panic. Let's try. 1 mile was 1,609 meters. Okay. Did I want meters? No. I want centimeters. How many centimeters are in a meter? Allow me. This is a meter stick. There we go. This is a meter stick. It is 1 meter long. Because you can't see, it's really close enough. But if you could see, you would see that there's 100 centimeters in this meter stick. So how many centimeters is in a meter? 100. So let's go back to our problem down here. We're going to do what? Disco down the unit. Yes, we are. Meters, disco down that unit. So put meters down here. What did I say? I said there was 1 meter. There's 100 centimeters. That's a 0. 100 centimeters in a meter. Cancel my units to check my work. To make sure I'm on track. All my units cancel. That's good. And I'm left with centimeters. Perfect. So what does that equal? I don't know. Let me get my calculator. Got it right here. Okay, so 6.2 times 1,609 times 100. And what's in the denominator? Just 1. So, wow. You know what? I'll have to put these on. Can't see. Wow, 997,580. So what is my answer? 997,580 centimeters. Probably way more information than you ever wanted to know. Okay, so let's go to the next problem. Let's see. Can I do that? I can do that. There we go. Do I want to? No, I don't want to do that. There we go. All right, next problem here. At 20 weeks, a zygote is about 17 centimeters. How many millimeters is this? Well, let's see. What is my given? No, it is not 20 weeks. Right, it's 17 centimeters. 17 centimeters is my given. Oh, hang on. Let me back. See, I told you I'm not great with technology. There we go. Let's do the pen again. There. You be patient with me. Okay, 17 centimeters is my given. What's my unknown? What am I trying to find? Millimeters. Okay, so I write my given, 17 centimeters. Ooh, there we go. Well, it looks like my black pen's running out of ink. Disco down. Disco down my unit right there. Centimeters here. Centimeters goes in the denominator. Okay. How many millimeters are in a centimeter? Okay. I'll cut you a break till you guys memorize it. 10 millimeters in 1 centimeter. And look, centimeters cancel. And I'm left with millimeters. There we go. Millimeters. Perfect. So 17 times 10, I can do that without a calculator. So 17 times 10, 170 millimeters. Ta-da! Okay, when eyes are dilated for an eye exam, they expand 5 millimeters. How many centimeters is this? Okay, what's my given? Yep, 5 millimeters. 5 millimeters. What's my unknown? Centimeters. So I start by writing my given, 5 millimeters. And then do what? Oh yeah, we disco down the unit. Put millimeters in the denominator. What am I trying to find? I'm trying to find centimeters, so I'll put centimeters in the denominator, or in the numerator, sorry, because I do know the conversion factor there. Up at the top, 1 centimeter, 10 millimeters. So, millimeters cancel. Okay, 5 times 1 divided by 10. If you said 2, don't say it out loud. It's not 2. 5 divided by 10 is what? 0.5 centimeters. Okay, so disco down is really fun. Here, let's see if we can get us off the pen. Now I don't want to keep that. There we go. And we'll see you for measurement day 3.